Hello everyone, I welcome you all to this 14th day of MATLAB Simulink Masterclass series. This is Malayapan from Pantech Solutions, and today our topic is induction motor speed control design using MATLAB Simulink. In this topic, we are going to discuss about what is the induction motor and what are all its types and how we can control the speed and how it is working. We can understand how we can understand the working principle and what are all the types of speed control mechanisms are available, how it can be implemented in the MATLAB. By implementing in the MATLAB, we can realize how the motor is actually controlled in the speed and it is utilized in the industry, industrial point of view. And finally, we will discuss about advantages and disadvantages of the machine along with the applications. And finally, you please keep engaged with the entire session. So we will discuss about the project, how we can choose our research projects and what all the areas are available. So those we will discuss in the last one. And if you take about the induction motor, so in this induction motor, so there are a variety of components are there. So one is called stator and another one is called rotor. So the stator has a winding and similarly rotor also has a winding. But in the winding aspect, again there are two types that we will check in the forthcoming slides. So here we are going to apply a supply to the motor, and for rotor automatically it starts to rotate. So in that aspect, we can call it as a single excitation system. So in this, if you take a electrical structure of the machine, so it has a stator winding, similarly rotor winding. In the stator winding only we are going to apply the voltage. So by applying this voltage, by mutual induction law, the voltage will be generated, the flux will be generated in the rotor side. So due to that action, the rotor has a resultant flux. Already by applying the three different phases to the motor, the stator has a resultant flux. So similarly, rotor also has a resultant flux. The stator will rotate in the frequency, that is 120 f by p, that fundamental speed. The stator will has the speed, its own reference speed. Similarly, rotor also has a reference speed, but with some difference will be there. So that difference is due to the air gap inside the motor and inside the motor between the stator and the rotor. So due to that air gap, that the flux linkage will get some differences. So due to that one, that rotor will try to catch the stator flux. Okay, so if you take this animation, stator has a resultant flux. Similarly, rotor also has a resultant flux. But the rotor will try to catch the resultant flux of the stator. It will not catch exactly, but it will always try to catch. So due to that principle, the rotor receive a force, and due to that force, the rotor will try to rotate and from the standstill position. So once if you apply the entire voltage to the machine, then the rotor will get to rotate. And here we are going to apply only the stator side. So that's why we are calling it is a single excitation. For some cases, for in the synchronous emission channel, we have to apply to the rotor also. Then only that rotor will get rotate. So that is called a dual excitation or double excitation mechanisms. And according to the types of the machine, so this motor will comes under that AC motor. Generally, actually in the previous session we have discussed about DC motor. So this session will cover of AC motor. Again, in the AC motor it has two types. One is called asynchronous machine and synchronous machine. The synchronous motor will rotate in the stator frequency, because the rotor and stator will lock interlinked with the particular frequency, that is a stator frequency. So that's why the slip will be 0. But in the case of asynchronous machine, rotor will try to catch the stator frequency, but it will not catch. So there will be some difference will be exit. So due to that, so we are calling this as a asynchronous machine. So again we can classify this asynchronous machine based on the number of phases. See, if you take a number of phases, one is a single phase and another one is a three-phase machine. Again, in the single phase machine, again for providing the different voltage, so here by using the capacitor we can split the phase from A phase to B phase, so that due to that it will give a resultant flux in the stator side. So due to that one, again we can get a mutual inductance on the rotor side. So due to that we can run the machine with the same principle. Again, in the three-phase system, by default, three voltages are available with 120 degree each of the 120 degree. Finally, we will get a resultant flux. So due to that resultant flux, the motor will start to rotate in the principle by mutual induction principle. And similarly, again we can further we can classify based on the rotor structure. Yeah, as per earlier our discussion. So based on the rotor sections, we can classify it as a squirrel cage induction machine. Similarly, wound rotor induction machines. In the squirrel cage induction, if you take a squirrel cage induction motor, so this is a squirrel cage induction motor. So in this motor, it has a two setup. One is called rotor. In the rotor conduction bar along with the end rings. So each conduction bar, inside the bar the copper will be there. So all the induction bar, so all the conducting bars as terminated with the end rings. So whenever the flux induced in the rotor, so there will be a current flow will exit. So due to that current flow and due to this end rings, the huge amount of current will get generated because the entire voltage, conducting bars has terminated. Then it's a short circuited. So due to that, we can generate a force. So similarly, that heat will be huge. So for that situation, people will use a heavy material to withstand the heat. So again, all the rotor winding will be terminated and short circuit with the short circuit connections. So again, the rotor will completely molded and then sealed with the complete bearings. Then we can finish the assembly complete assembly, and then we can start utilizing this motor. But in the case of wound rotor types, so all the instead of end ring, so here the slip ring will be there. So that slip ring we have to connect externally with the rheostat. So by changing the rheostat position, we can adjust the speed. And finally, the rheostat end other terminal needs to be terminated with a common point. So either it may be neutral point. So by providing this additional assembly, so we are calling this as a wound rotor or slip ring induction machines. So by wherever it needs, then we can use. But in industrial point of view, majorly people will use for the slip ring induction machines. So according to that, our speed control mechanism. So here we can take again as per the theoretical point of view, variety of methods are there. But here we are going to discuss about, in this session we are going to discuss about squirrel cage motor. How for this squirrel cage motor, how we can adapt these mechanisms. So first we will take a variable frequency and variable voltage. Based on this fundamental formula, speed is equal to 120 F by P. So this is the fundamental formula of this induction machine. So in this machine, in this equation, F and speed is directly proportional. Whenever you adjust the speed, whenever you adjust the frequency, then we can control the speed. So how we can adjust the frequency? So by default we have a 150 Hz only. By implementing inverter along with the PWM generator, then we can adjust the frequency. By changing the PWM generator frequency, then we can change the machine speed. Similarly, if you adjust the pulse width, then we can adjust the voltage to the machine. So in that way, we can get a variable voltage. And the third one, how variable voltage and variable frequency. So the variable voltage and variable frequency is nothing but, so here you have to adjust the magnitude as well as the frequency. In that case, you can get a variable voltage and then variable frequency. Similarly, according to the basic formula, so there is a constant called V by F constant. See, if you keep this constant, if you keep this parameter as a constant for entire speed range, then we can increase the machine's performance, right? So there again we can improve the efficiency of the machine. So that we will discuss in that future. So about the demonstration. But here we are going to check the three demonstration: variable frequency, variable voltage, and variable frequency, variable voltage method. If you take let us go for the demonstration. So here in this demo we are going to discuss about variable frequency. Either we can use a 120-degree mode or 180-degree mode. Similarly, variable voltage method, for this one we are going to use sine pulse width modulation. So the same PWM generation for variable voltage and variable frequency method. Similarly, we can develop one closed loop method. So how the speed will be adjusted for our reference speed. So let us open the MATLAB, open the Simulink. So open the new folder, open the new simulation file. So here first we have to take a motor, right? So let us take a AC machine or asynchronous machine. Yeah, so this is asynchronous machine, SI unit, take SI unit. So here all the parameters will be there. So based on our types we have to use. So let us take a squirrel cage, and default parameter will be there. You have to choose the parameter. So here again both the 60 Hz and 50 Hz systems also there. You can choose whatever you want. So now I am going to use 50 Hz system. Yeah, so now I have chosen the 50 Hz system, and again I am going to construct the inverter. So how we can see the how we can construct inverter for this system. So let us check. So before that, please save the system, save the simulations. Just to save the simulation. It's taking some time. Yeah. Let's save the simulation. For this we need a three-phase inverter network. So for that we need to take a MOSFET. Yeah, so this is a MOSFET. Just remove the measurement block, unnecessary components. For ZCS, ZVS applications we can use the block facility. So let us take a three-phase network. Just to connect as per the diagram. And again this inverter you can connect with a rectifier. That is, by default we cannot get a DC power supply. So from the AC power supply only we can get it the DC power supply. But in the simulation we can use the DC power supply, not an issue. But in the real-time applications you have to construct a rectifier and then filter. Then only you can get a DC bus voltage. But for this simulation we are going to use the direct DC voltage for the input to this inverter. And again we need a PWM generator. So for the PWM generator we need a pulse generator. So this inverter, this induction motor is going to work under 50 Hz system. So for that we need to identify we need to define the frequency. So that frequency is the 50 Hz frequency. So take a pulse generator block. So this pulse generator we have to define the frequency. First we have to define the frequency. Now we are going to define as a 50 Hz. So for the 50 Hz and the pulse width is a 50%. if you keep this as a 50%, then it's going to work in 180-degree mode. It's being a simulation, no need to worry about the dead band, so it won't give you any issues, because the MATLAB will take it as an ideal switch. And for second switch, then we have to divide, or we have to phase shift for 1/6 of the period. So for that one, so this is one period. So just divide to sixth one. So divided by 6, keep it divided by 6. Then we can phase shift to second 1/6 of the period, so that we can generate a PWM after the after mode 1. So exactly. So if you take let us identify the go to block. If it is a S1, let us name it as S1. Yeah, so the S1 is generated, so connect the S1. Similarly, we have, this is for S2, right? So here, as per our circuit, so the S2 switch is, so S2 switch is here. So this is the S2 switch. Similarly, S3. So for S3, again we have to increase the phase delay. So just multiply with this delay period for mode, for each and every mode. If you have a calculation issue, please go to MATLAB. Our system is a 50 Hz, so for time period is 1/50, and for 1/50 divided by 6, this is the one more time period. So again for second the third switch, take it as a 2 into 1 divided by 50 divided by 6. So this is the actual time phase delay which I have used in the pulse generator block. So this is for S3. Just change the name S3, and so this is in the inverter circuit. This is the S3. Similarly, we have to generate a PWM for S4. So S4, so 3 times of the phase mode delay. So let us take 3 times. Otherwise, you can keep, if you keep this value, so here you will get a fractional value, right? So if you truncate it, then again exactly half of the cycle will be there. So here yeah, so you just select, and S3 needs to be connected, sorry, S4 needs to be connected. Name it as S4. So this is a S4 circuit, and again we have to create a PWM for S5. Take it as S5. For S5, just change 4. That's enough. So change the name of the block S5, and now we have to generate a from block. So this is a from block. This is a S5. Just rotate it. For rotations, just press Ctrl R, and similarly S6. For S6, just change the value here 5. So make it as S6. So this is S6 block. Yeah. So now we have developed the inverter pulse with the PWM. We can verify the inverter operation and then motor speed operations. So connect inverter. This is a phase. Just to connect with the A phase. Similarly B phase and C phase. And for torque value, just apply with the constant data, constant block. So here we are going to check the speed of the machine. So just to keep constant value 1. Take a DC voltage source. So this DC voltage source, yeah, so this is the DC voltage source. Here if you take a machine ratings, so in this machine rating they have clearly mentioned 400 voltage AC. So to get a 400 voltage here, either we can get a 600 voltage, right? So that is the maximum voltage range. See, 400 voltage AC we should apply. So for that one we have to apply 565 or 600 voltage. So let us keep 600 voltage DC bus voltage. So the PWM has been applied, and then now we have to verify the motor data. So for that one we need a bus selector block. So if you connect the bus selector block, then all the motors measurable data we can get it. So for that one we need a motor speed. First we need to motor speed, and then torque. If you need, you can use the torque, and similarly rotor voltage, rotor current. Let's take a rotor voltage. Rotor voltage, actually here VDQ only one is there. So by keeping the additional multimeter, we can check the rotor voltage. Now again voltage measurement block. Just to connect a voltage measurement block. Again here in the basic simulation, here you can use one DC power supply. By adding the two splitted DC power supply filter capacitor, we can get a neutral power supply also. Take a scope. So with this scope, just increase the number of inputs. So here this is the number of input. Already we have a 4 unit, and then 3 datas along with the DC stator voltage. So we can get so first we can verify the stator voltage and rotor speed, then torque, and then current. So like that we can measure it. And now we need to add a power guide block. Take a power guide block. So this is the syntax of the MATLAB Simulink. Just to change it, whatever you want you can adjust it. So again change the simulation time. Save the simulation. If you run the simulation, so it's again basic speed control mechanism of the induction motor. If you run the machine, so we can understand the motor data. Again, simply instead of inverter, you can connect a 3-phase AC voltage. So here by default 3-phase AC voltages are there. So by connecting that one also, you can verify the motor data, whether your motor is perfectly running or not. Before start working with the inverter, please connect AC default AC voltage source, so that I will show you. Then you can understand basics of the motor. Just to change the scope data so that you can understand what it is. Just apply all the signals so that you can get a better clarity. See here, just adjust the entire graph. See here, we can understand this is the face-to-face voltage. If you want to get a neutral voltage, face to neutral VAN, then it will be a 2 level. So that will be a stepped voltage. So here this is a phase VAB voltage. So that's why we are getting this voltage. If you convert to the 120 degree mode, you will get a additional level also. And so this is the rotor speed. So initially it's oscillating huge, and finally it's settled at one speed. And similarly, by general theory is induction motor needs a huge starting current. So this is the induction motor starting current, because the rotor is terminated with the end rings. So in that conditions, the entire short circuit will get entire rotor current will get short circuited. So there it needs a more amount of current to start the machine. So that's why this is the that's why during this transient period, the rotor stator requires a more amount of current. So again, transients of induction machines or transients of the motor is again a research area. You can do lot of research with the transient behavior of any electrical machines. So this is a 120 degree mode. So here all the simulations we can get. If you change the frequency, see here, based on the frequency, if you convert it to it's a radian per second. If you add this P by 130 by P, you can take it as RPM. Just add here 30 by P, 30 by pi. If you add this block, so you can get a speed curve in the RPM. So now the idea is, so we have to increase the speed, right? So here we have applied only the constant frequency. So we have clearly mentioned in the program, so 50 hertz. So if you change the frequency, so the motor is running about 1500 hertz. If you decrease the frequency, so decrease the frequency is nothing but here you have to adjust the value. See here you have to adjust the value. If you decrease the frequency, we can reduce the motor speed. So just a change, instead of 50, you can keep it as a 40. So again, the duty cycle is same. Again, you have to apply all the things called here also you have to change, because the phase delay must be changed. Here are the 40 hertz, and then switch 3, similarly switch 4, here we have to change switch 4. For switch 5 also we have to change. For all the switches we have to do this modification. See, we are reducing the speed. So in that conditions, again the motor should run at the lower speed. Yeah, see here we have reduced the motor speed. So now reduce the motor supply frequency. So now the motor should run at the lower speed. See here the 1500 was the speed. Now about the 1250 will be the 250 is the speed. So like that we can change the we can control the motor speed. So this is a variable frequency method. So again, if you want to if you want to control your motor with a variable voltage method, then we need additional block, additional PWM generation, so called sine pulse width modulation. So for that we need we have to generate a sine PWM signals. So let us take this PWM blocks. So let us take a repeating sequence. So first we have to develop sine pulse width modulation, right? So for sine pulse width modulation, carrier wave is mandatory. So just to take a carrier wave, for that one we can identify, we can design sine carrier wave with the help of this repeating sequence block. So this is output values are the y-axis. So this is the repeating sequence. Now the repeating sequence generated the triangular wave. For that one we can verify the scope whether this generated or not. If you run the simulation, here we can verify the carrier wave whether it has generated properly or not. Yeah, so somehow it's generated. Yeah, so perfectly that the sine carrier wave generated. Now we need a reference waveform. So let us take a sine wave. This is one of the method. So here we can verify the amplitude and other things, frequency. So let us take a 2 star pi into 50. So here the 50, that is the frequency here measured, and similarly phase radians, radians. So that also here we can mention. So for 120 degree, so again we need 3 phases. So here I am going to get minus 120, and sorry, this is for B phase is a 120 degree, not a minus 120, and this is the C phase is a minus 120. So we have to verify this also. So save the simulation and then run it. Then you can get the output. So now we are getting the result just in Logit. So you will get to know whether we have generated properly the 50 Hz system. See here again the phase difference is there. So now we have to add. So along with we have to add a 2 pi. by pi we should add. First we will verify the frequency. Just verify the frequency. Now you can understand the waveform generation. Yeah. See A phase exactly generated, and then 1 hertz, for 1 period, A phase blue line has generated perfectly, it's working. Similarly, we have to generate a B phase. Now we have to introduce the phase shift. See, actually, this is the A phase, the frequency has been generated. So for the A phase, we have to add for 120 degree into pi by 180. Pi by 180. So if you add this one, then we can generate exact phase displacement. Pi by 180. So that we can get an exact three phase shifted PWMs. Yeah, see here A phase, and then similarly B phase and C phase. See here. So 3 phases are generated. Now we have to compare with the carrier waveform. So here, just to connect here, take a relational operator. If you compare any logic, you can use it. If you compare above the, see, take A phase and compare with the triangular waveform. So this is the PWM for S1, and for S again, if you invert the PWM, so for that one again you have to change the logic similarly, because it's a unipolar pulse width modulator carrier. So let us check. By default it will gives you the output, not an issue at all actually. But better you can keep again you add additional carrier waveform. So I'm going to take a logical operator. So for logic operator, take a NOT gate and apply it to the gate pulses. Yes, so this is for S4, right? So now again we have to generate a C phase. So C phase is a 240 degree. So take a minus 120 or 240, just to take it. So take this value graph, compare with the carrier waveform, and straight away for again this is the S2. If machine we have to change the sequence also if not run, if machine is not running it. Change the speed and invert to the fifth one. Yeah, and similarly connect a 3-phase third one. And take a carrier pulse and connect B phase here. So now we are going to connect the generator PWM for B phase. So here that pulse is for third switch, and this is for sixth switch. So now the PWM is ready for the 3-phase inverter. So for that one, we have to verify all the PWM pulses. This is VBA, Similarly, we have to connect BC. Sorry, CA. Take a scope. Then we have to run the machine at least 1 to 2 seconds so that we can generate a signals. Just to save the simulation before it starts to running. Then run the machine. Run the simulation. So here, if you again here you have a parameter to adjust the magnitude as well as adjust the frequency. See here, earlier method we have only one parameter called the frequency parameter. So by changing that frequency, then we can directly control the speed. So here we are having two parameters called the magnitude. So how the magnitude can be adjusted? So this is the magnitude, amplitude value. This is the magnitude. So by changing this value, then we can adjust the voltage. Similarly, by changing the frequency, see here the f is the frequency 50 Hz. If you change the frequency, then we can adjust the speed. So we can control the speed. Let us verify the motor behaviors. See here, almost the PWM has been generated. So similarly, the current and the voltage and the torque of the machines, everything has been it's available. So here, if you adjust the amplitude, so if you take a point instead of 0.5, if you take a 1 instead of if you keep 0.6, then we can somehow change the speed. So not a complete range. Somehow we can change. So here only that V by F concept is going to apply. So so you have to, while changing the amplitude of our voltage, at the same time you have to change the frequency also. Then only that machine will run at under that V by F mode. Otherwise, it won't run on the V by F mode. Yeah, if you run the simulation, then now your motor will get a lesser speed. So because we have reduced the magnitude of the voltage, somehow it can be adjusted, not a complete thing. So by changing the frequency only, we can get a various range. Almost small speed has been controlled. And similarly, so yeah, see here earlier it was 1500, so now it is reduced. Somehow it is reduced, 1450 it is reduced. So similarly, we can change the frequency. So if you have a frequency value, then we can adjust the frequency. So by this method, we can control variable voltage as well as the variable frequency. So we have again one more demo is there. It's called a closed loop. Yeah, so take this simulation. It's the same method. See here, that entire the entire PWM is generated here. So with this method, the motor speed is taken as a reference speed. So by comparing with the actual speed, so the error we can get. So this error will generate a reference frequency of the PWM. So by this parameter, we can generate a three phase magnet reference voltages. So if you integrate this speed, you will get a theta. So by this theta, we can add three data. So this is an array input. So for 0 with omega t with 0 value and omega t with 2/3, that is 1/3 of the cycle, and similarly the third cycle. So by this way, you can add this trigonometric function. This is a cosine and sine function, sine block. So this input figure, the U is the input input signal one. So this is whatever the input signal, it will add together and then multiplied with the sine data. So then this is called the sine 2 pi omega. So that is the omega value. So by this way, if you increase it, then you can get the data for three difference. Just to start download this function in the download this file in the LMS portal, you can start using that one. So by this method, we can get a controlled mechanism for the adjusting the speed. So now this is 1450 is the reference speed. So now I am going to run the machine. So just wait for 2 seconds, it will give you the data. So it's keep on running. So in this by this method, we can change the motor speed with our reference speed. So this is, I mean, in industrial point of view, people are keeping one potentiometer to change the speed. So this is the exact algorithm for that applications. Just wait, just hold for 2 seconds, it will give you the results. See here, I am going to change the reference speed. So this is a 450 is the reference speed. If you change the reference speed into 500, then we can receive the speed. We have to allow the machines to run at its range. Then we can change the speed. So it will take some time because induction motor will have a transient behaviors due to the rotor bar short circuit. See here, if you increase to 2460, so like this we can add the control mechanism. So for hard, you can download the entire code into that hardware for Arduino, just removing all the power system blocks. See here, you have to remove all the sim power system block, but here this is the input for the, I mean, here straight away you can keep it as input for the Arduino controller, and then by adding this entire thing, it will work. But for additional components, you have to remove all the additional components you have to remove while for hardware code simulation. See here, whenever you change the reference speed, then it will gives you the variable speed value. So by keeping this mechanism, you can run it, and then you just download the simulation from our LMS portal and then start self-practice it. So by this three speed control method, we can use we can understand and we can realize we can understand the motor speed mechanisms. See here, so the advantages of the induction motor is, it's a very simple constructions, and again it's no need of maintenance. If you apply the DC motor, then you have to maintain the slip ring, commutator brushes. So in that case, Here there is no any like that like additional components, so we can, the maintenance will be very easy. And similarly, that application point of view, again single phase sensor, these are all some applications we can use for low range of applications, gardening equipments, and then basic household equipments, and even our household equipments previously we have used for fridges, washing machines and everything. But now they have moved to that BLDC, and then servo AC servo motors. For the, in the case of single three-phase machines, somehow high power applications. So these are some high power applications. So you can use it. And for project idea, here I have listed some ideas. So with this segment, we can choose our topic. For advanced power electronic circuits called front-end rectifiers, matrix converters, multi-level inverters, these are all the project areas. There you can, if you work a lot, then definitely your work will be, it's a highly appreciable topic. And if you choose in this area, definitely you can explain in your future, you can use it, those projects in your future career. And similarly, special machines controlling like a switched reluctance motor, synchronous reluctance motor, BLDC, then flux machines, linear induction motors. So these motors, if you choose the topic, then definitely it will be highly valuable concepts. And if you need custom applications, custom requirements, you please contact our people. Via the sales at pantech.mail.com and 9003113840. So if you connect this number, it's an Indian number, you can connect via WhatsApp, then definitely people will help you to for your custom applications. Start using this facility from Pantech Solutions. And if you have any clarifications, you please comment it, then I will try to give you the answers as soon as possible. So thank you for your valuable